Welcome back. In this lecture I would like to work out some example problems. Before I start discussing these problems, let me give the stepwise procedure for solving these problems. This is the suggested procedure. The first step is obviously you have to read the problem carefully and list the input data, and the second important step is you draw the sketch of the system and the cycle on TS or pH charts and label all the state points. And step 3 is obtain property data for all the state points either from the input or from property database or from property relations. And step number 4 is obtain the required output parameters by applying relevant mass and energy balance equations across the components or system. Finally, you have to check the units for consistency. So, if you proceed in a systematic manner, solving these problems will be very easy. Okay, so systematic procedure is always better. So, now let us go to some of the typical problems. The first problem is on air cycle refrigeration system. The problem statement is like this: a closed air cycle refrigeration system based on reverse Brayton cycle incorporates a regenerative heat exchanger which has an effectiveness of 0.8. The temperature and pressure of air at the exit of low temperature heat exchanger are -30 degrees centigrade and 100 kilopascal respectively, and the temperature of air at the inlet to compressor is 10 degrees centigrade, and the pressure at the exit to the compressor is 1000 kilopascals. This is the problem statement. It is a simple air cycle refrigeration system. Only one change is there is an additional component, that is a regenerative heat exchanger. It is also mentioned that we have to assume no frictional pressure drops and compression and expansion processes to be reversible and adiabatic, and under these assumptions and from the given data we have to find the required mass flow rate for a refrigeration capacity of 100 kilowatts, a required volumetric flow rate of air at compressor inlet, and the system COP. And for calculation purposes we can assume air to be perfectly dry with a specific heat Cp of 1.005 kilojoule per kg Kelvin and specific heat ratio gamma of 1.4, and gas constant for air you can take it as 0.287 kilojoule per kg Kelvin. And the second part of the problem is we have to compare the performance of this system with a system which does not have a regenerative heat exchanger. That means you have to compare this system with a simple system which does not have a regenerative heat exchanger. And for the simple system, the input data is the temperatures and at the compressor and turbine inlet are -30 degrees centigrade and 20 degrees centigrade respectively, and pressures are same as before, that is 100 kilopascal and 1000 kilopascal. Now, this figure here shows the schematic of the system. So, you can see that we have the 4 basic components, that is turbine, compressor, low temperature heat exchanger where the refrigeration is produced, and the high temperature heat exchanger where heat rejection takes place. In addition to these 4 basic components, we have an additional component, that is the regenerative heat exchanger. Now, if you look at the schematic, you can understand the purpose of regenerative heat exchanger. The purpose of regenerative heat exchanger is to pre-cool the air that is going to the turbine. That means the air that is going to the turbine, that is 0.5, will be pre-cooled if you use a regenerative heat exchanger. How is it getting pre-cooled? It gets pre-cooled by rejecting heat to the cold air stream that is going to the compressor. So, you can see that in the regenerative heat exchanger, cold air coming from the low temperature heat exchanger extract heat from the hot air that is going to the turbine. Okay. So, as a result you are able to pre-cool the air that is going to the turbine, and we will see that when you pre-cool the air, the temperature at the inlet to the low temperature heat exchanger will be reduced. So, this is the purpose of using a regenerative heat exchanger. Now, let me show the cycle on TS diagram. As I said, the second step is to show the cycle. So, here I am using a TS diagram, and let me explain the various processes. Let me begin at this point. This is the inlet to the compressor. So, the air is compressed reversibly and adiabatically. So, entropy remains constant during this process. So, this is the reversible and adiabatic compression. Okay. and during this process the pressure increases from 100 kilopascal to 1000 kilopascal, and you can also see that temperature is also increasing because of the compression. Okay. Next process is process 3 to 4. Process 3 to 4 is the heat rejection process in the high temperature heat exchanger. Okay. So, this is the heat rejection process in the high temperature heat exchanger. During this process the pressure remains constant, that means it is an isobaric process. So, pressure does not change. The temperature reduces because it is rejecting heat to the external heat sink. Then process 4 to 5 is the heat exchange process that is taking place in the regenerative heat exchanger. So, in this process the temperature drops because the hot air exchanges heat with the cold air that is coming from the low temperature heat exchanger. Okay. So, as a result during this process the pressure or temperature reduced from 4 to 5, whereas the pressure remained constant at 1000 kilopascal. And the process 5 to 6, this process is isentropic expansion in the turbine. So, during this process, as you can see, the pressure reduces from 1000 kilopascal to 100 kilopascal. As a result the temperature drops. Okay. And since this is an isentropic process, the entropy remains constant. Okay. And finally process 6 to 4 is a heat this process 6 to 4 is the actual heat extraction process, during which you get the useful refrigeration. Okay. And this is again an isobaric process. This process is taking place at 100 kilopascal pressure, and during this process, because of the heat transfer to the air temperature increases from 6 to 1. Okay. So, this is the process, and finally process 1 to 2. Process 1 to 2 is what is taking place in the regenerative heat exchanger. As I have already explained, during this process heat is transferred from the hot air, that is from 4 to 5, to the cold air, that is going to the compressor. As a result the temperature increases, whereas the pressure remains constant. So, these are the 6 processes in this cycle. Now, let me from the input data we know that the temperature at this point, that is at the exit of the low temperature heat exchanger, is minus 30 degrees centigrade. We know this temperature. Okay. And we also know the pressure. So, immediately we can locate this point, and it is also given that the temperature at the inlet to the compressor is plus 10 degrees centigrade. That means this temperature is also given. Since this pressure is also same as 100 kilopascal, we can also locate this point. That means this point is known to us and this point is known to us. Now, we have to find out remaining points, state points. First, let us look at point 3. How do we find the point 3? We know that this process is isentropic compression process. So, for this process we can write one equation as P2 V2 to the power of gamma is P3 V3 to the power of gamma. This is one equation, and for each point we can write for example P2 V2, we can write it as RT2 because we are assuming air to be an ideal gas. Similarly, you can write P3 V3 is RT3. Okay. So, these are the equations. From these equations we have seen that you can finally write for this process, if you are eliminating specific volume for this process, ultimately you can show that the temperature T3 by T2 is given by P3 by P2 to the power of gamma minus 1 by gamma. Okay. This is the expression which relates the temperatures with pressures, and we know the pressures. P3 is known, P3 is nothing but 1000 kilopascal, P2 is known, which is equal to 100 kilopascal. So, this side we know, and gamma is 1.4, and T2 is known to us, which is given as the input. So, for using this equation we can find out what is T3. Okay. Then comes point 4. How do you find the temperature at point 4? Then temperature at point 5. Okay. Temperature at point 4 and 5 will be found using the effectiveness of the heat exchanger. Okay. That I will explain a little later. So, these 2 points will be obtained using the effectiveness of heat exchanger and the energy balance across the regenerative heat exchanger. Okay. And for the process 5 to 6, which is this process is again an isentropic expansion process. So, again we are similar to isentropic compression, we can write for this process T5 divided by T6 is equal to P5 by P6 to the power of gamma minus 1 by gamma. Again P5 and P6 are known, P5 is 1000 kilopascal, P6 is 100 kilopascal. So, this right hand side is known to us, and from the left hand side if you can find out T5, you can find T6 using this expression. Okay. So, this is how we will be finding the different state points. Okay. So, the given information is like this. QL is 100 kilowatt and effectiveness of the heat exchanger is 0.8, and the low side pressure, that means the suction pressure is 100 kilopascal and the discharge pressure is 1000 kilopascal, and temperature T1 is minus 30 degrees centigrade, that is 243 Kelvin, and temperature T2 is 10 degrees centigrade, that is 283 Kelvin. And for A the properties are given as Cp is 1.005, gamma is 1.4 and R is 0.287 kilojoule per kg Kelvin. Okay. So, as I have already explained, let us find out the temperatures at various points. First, the temperature at the exit of the compressor. As I have already told you, this is an isentropic compression process. So, temperature at the exit of the compressor we find by using this equation, T3 is equal to T2 into P3 by P2 to the power of gamma minus 1 by gamma, and if you substitute the values you find that T3 is 546.4 Kelvin. Now, we have to find out other temperatures T4, T5 etc. For this, as I told you, we will be using the definition of heat exchanger effectiveness. From the definition of heat exchanger effectiveness, how do you define that? Let me explain. So, here for this one I am talking about the regenerative heat exchanger. You can define effectiveness as Q actual divided by Q maximum. Okay, and Q actual is the actual heat transfer between the two streams, which is given by, for example, if you are taking the cold stream, Q actual is nothing but mCp into T2 minus T1. Okay, mCp into T2 minus T1, where m is the mass flow rate of air, Cp is the specific heat, T2 and T1 are the exit and inlet temperatures. This is the Q actual. What is the Q maximum? Heat transfer rate will be maximum when the exit temperature T2 is equal to T4. So, this is the condition under which the heat transfer rate will be maximum. That means Q maximum is equal to mCp into T4 minus T1. So, same mass is flowing, mCp get cancelled. So, finally, you find that effectiveness of heat exchanger is given by T2 minus T1 divided by T4 minus T1. Of course, you can also write this in terms of the hot air stream, or that means you can write this also in terms of T4 minus T5 divided by T4 minus T1. Okay, so you can use either this expression or this expression. So, from that expression, delta, as I have already told you, effectiveness is delta T actual by delta T maximum, and that is given to be 0.8. Delta T actual is T2 minus T1, T2 is 283 Kelvin and T1 is 243 Kelvin. So, the delta T actual is 40 Kelvin. From this you can find out delta T max, which is equal to T4 minus T1, that is equal to 40 by 0.8, that means 50 Kelvin. So, from this you can find out T4 because T1 is known to us. Okay, so, T4 is T1 plus 50, that is 293 Kelvin. Now, what we do is we have to find out the temperature at the inlet to the turbine, that is 0.5. For that we apply the energy balance across the regenerative heat exchanger. This is again very simple. If you are assuming steady flow across the regenerative heat exchanger and take a control volume across the regenerative heat exchanger, and if you apply the energy balance is energy gained by the cold stream is equal to energy lost by the hot stream. Okay, so energy gained by the cold stream is nothing but mCp into T2 minus T1. This should be equal to energy lost by the hot stream, which is equal to mCp T4 minus T5. So, in for this cold air standard cycle analysis, Cp value remains same mass is flowing. So, these values get cancelled. So, finally, from energy balance we see that T2 minus T1 is equal to T4 minus T5, and T2 and T1 are known to us, T4 we have computed. So, from this we can find out T5. That is what is done here. T2 minus T1 is equal to T4 minus T5, that means T5 is equal to T4 minus 40, because T2 minus T1 is 40. So, from this we get T5 as 253 Kelvin. So, finally, we have to find out what is the temperature at the exit of the turbine. Okay. So, this process, as I have already told you, is an isentropic expansion process. So, temperature at the exit of turbine is given by T6 is equal to T5 into P6 by P5 to the power of gamma minus 1 by gamma, and T5 just now we have found is 253 Kelvin, and P6 is 1000 kilopascal and P5 is 100 kilopascal. So, if you substitute these values, you find that T6 is equal to 131 Kelvin. Now, mass flow rate of air we have to find out. Mass flow rate of air is simply given by refrigeration capacity by Cp into delta T. This you get by applying energy balance across the low temperature heat exchanger. So, from energy balance across the low temperature heat exchanger, QL is equal to m dot into Cp into temperature rise, that is T1 minus T6. Okay, so, from this you can find out what is m dot. Okay. So m dot is given to be 0.8884 kg per second, QL is given as 100 kilowatts, Cp is 1.005 and T1 and T6 are known to us. Okay. Next is we have to compute the volumetric flow rate at compressor inlet. So volumetric flow rate at compressor inlet is simply equal to mass flow rate into specific volume of air at that point. And since we are assuming the air to be perfect gas, specific volume of air is given by P by RT at compressor inlet. That means ultimately the volumetric flow rate V is equal to M divided by P2 by RT2. Okay, where P2 is the suction pressure, that is 100 kilopascal, R is the gas constant, and T2 is the inlet temperature, which is equal to 283 Kelvin. So if you are substituting these values, you will find that volumetric flow rate is given by 0.7216 meter cube per second. Finally, we have to find the COP of the system. COP of the system is given by QL divided by W net, that is the net work input to the system, and net work input to the system is equal to work input to the compressor minus work output from the turbine. Okay. This you can easily find out by again applying energy balance across turbine and compressor. If you are applying energy balance across the turbine and neglect delta KE and delta PE, that means delta KE, delta PE are negligible for both the components. Then from energy balance, and this is a reversible adiabatic process, there is no heat transfer. So you find that work output from the turbine, okay, is simply equal to m dot Cp into T5 minus T6. Okay, this is from the energy balance across the control volume. Similarly, work input to the compressor WC is equal to m dot Cp into T3 minus T2. Okay, so m dot Cp is same. So the net work input is nothing but the work input to the compressor minus work output from the turbine. You can see that the turbine is supplying its useful work output to the compressor. Okay, so net work input is the difference between these two. So that is what is written here, W net is equal to Wc minus Wt, that is equal to mCp into T3 minus T2 minus T5 minus T6. All the temperatures are known to us. So if you substitute these values, you will find that net work input to the system is 126.25 kilowatt. Therefore the COP is QL divided by net work input, that is 100 divided by 126.25, that comes out to be 0.792. Okay. So this is how we can calculate the required performance parameters. So you can notice that first we have drawn the system schematic, then we have drawn the cycle and TS diagram, because here TS diagram is more useful. Then from the given information we have obtained the state points, properties at all other state points, and once you have the properties at all the state points, all that you have to do is apply proper mass and energy balance equations across each component or across the system and find out the required parameters. Okay. Now the second part of the problem is we have to compare the performance of this system with a system which does not have regenerative heat exchanger. Okay, that means a simple system. So a simple system, I will just show the TS diagram. You can see that in a simple system, cycle is given by, this is the simple system, okay, 1, 2 dash, 4, 4 dash. Okay. So again you have isentropic compression, isentropic expansion, and isobaric heat rejection, isobaric heat extraction. Since you do not have any regenerative heat exchanger, there is no heat exchange between hot and cold streams. Okay. And we know from the given input information that this temperature is minus 30 degrees centigrade and this temperature T4 is 293 Kelvin. Okay, so these two temperatures are given, we have to find out the remaining temperatures, and since the pressures are same 100 kilopascal here and 1000 kilopascal, we can find out T2 dash is nothing but T1 into P2 dash divided by P1 to the power of gamma minus 1 by gamma. Similarly T4 dash is T4 into P1 by P1 by P4 to the power of gamma minus 1 by gamma. All the pressures are known, T1 and T4 are known, so we can find out T2 dash and T4 dash. Okay. So that is what is done. So from that you find that the temperature at the exit of compressor is 469.16 Kelvin, temperature at the exit of turbine is 151.76 Kelvin, and mass flow rate of air again from energy balance across the low temperature heat exchanger is 1.0906 kg per second, and volumetric flow rate is 0.7606, and finally COP of the system, you find out the net work input, which turns out to be 93.08 kilowatts, and COP is found to be 1.074. Okay. So this is the performance without any regenerative heat exchanger. Now we can quickly compare the performance with and without regenerative heat exchangers. You can see that when you are using a regenerative heat exchanger, temperature at the exit of compressor is much higher compared to this. Okay, this is a drawback actually. But what is the advantage of using regenerative heat exchanger? Temperature at the exit to the turbine is much less compared to the one without regenerative heat exchanger. This is 131 versus 151. As a result of this, the refrigeration effect increases. Since refrigeration effect increases, required mass flow rate reduces when you are using a regenerative heat exchanger. That is what you can see. Okay, and the required volumetric flow rate also reduces. That means basically you will be handling less amount of air. Okay, of course the penalty you will be paying is in the form of higher net work input because of the higher temperature at the compressor exit. Okay, you can see that net work input is much higher compared to the system without regenerative heat exchanger. As a result, the COP of the system with regenerative heat exchanger is less compared to the system without regenerative heat exchanger. So basically you have to make a trade off between the mass flow rate, the volumetric flow rate and COP, okay, and justify the use of regenerative heat exchanger, right. So this is a way to solve the typical problems in refrigeration and air conditioning. Okay, so based on this problem I will give you a homework problem, you work it out. Okay, the homework problem is like this. You work out the above problem just by replacing air with helium gas. Okay, so rest of the data remains same. All that you have to do is you have to replace the working fluid with helium gas. Okay, and for helium gas the properties are like this. The specific heat Cp is given as 1.193 kilojoule per kg Kelvin, and specific heat ratio is 1.667. Okay, I will give you the answers in the next class for this problem. So the second problem is like this. This is a Vapour compression refrigerant system, problem on Vapour compression refrigerant system. A problem statement is like this: a domestic refrigerator based on refrigerant R134A operates at an evaporator temperature of -23.3 degrees centigrade and a condensing temperature of 54.4 degrees centigrade. At these conditions, the required refrigeration capacity is 100 watts. Assuming a saturated single stage cycle and a compression process with an isentropic efficiency of 0.65. So this is the information given. Refrigerant is specified, temperatures are specified, capacity is specified, and the efficiency of the compressor is also given. From this information we have to find out required refrigerant mass flow rate in kg per second, volumetric flow rate at compressor inlet in meter cube per second, quality of refrigerant at evaporator inlet, void fraction at evaporator inlet, actual power input to compressor in kilowatts, compressor discharge temperature, actual COP, and finally the cycle or second law efficiency. So this is the list the information given. Information given is like this: refrigerant is R134A, refrigerant capacity is 100 watts or 0.1 kilowatts, and evaporator temperature is -23.3 degrees centigrade, and condensing temperature is 54.4 degrees centigrade, and the isentropic efficiency of the compressor is 0.65, and it is mentioned that it is a standard single stage saturated cycle. Okay. That means you have the 4 basic components. Since it is a standard cycle, you have the evaporator, compressor, this is the condenser, and this, as you know, is expansion device. And this temperature is specified, evaporator temperature -23.3 degrees centigrade, and this temperature, condensing temperature, is specified 54.4 degrees centigrade, and it is a saturated cycle. So the exit condition, this is saturated vapor, and this condition, that is at the exit of the condenser, is saturated liquid. Okay, so this is the information given, and this compression is not ideal. So you have an efficiency for the compressor which is given by 0.65. Okay. So now using refrigerant property data, let us find out the required properties at various state points. Let me quickly explain how to find out the properties. Okay, what is that we know, and how do you find the rest of the properties? All that we know is, we know that the evaporator temperature, okay, TE is -23.3 degrees centigrade, this is given to us, and the condensing temperature TC is 54.4 degrees, this is also given to us. And we also know that the exit of the evaporator, that is point 1, is saturated vapor, and exit of the condenser 0.3 is saturated liquid. So, this is the information given to us, and it is also mentioned that the isentropic efficiency of the compressor is 0.65. Okay. What do you mean by isentropic efficiency of the compressor 0.65? That means the actual compression process 1 to 2 is non-isentropic, whereas 1 to 2 dash is isentropic. And from the definition of isentropic efficiency of the compressor, you can write the isentropic efficiency as isentropic work input divided by the actual work input. So, from energy balance, this is nothing but H2 dash minus H1 divided by H2 minus H1. This is given to be 0.65. Okay. So, this is the information that we have, right. So, from this information, how do you find the state properties, various enthalpies, temperatures at various points? So, let us begin with the saturation line, that means 0.1 and 0.3. Okay. This point is already fixed because we know the temperatures, and we also mentioned that this is a saturated condition. So, on the saturated line, specifying any one parameter is enough. Okay. So, once you say that it is saturated vapor and temperature is specified, we can immediately locate the point and find out what is the enthalpy H1 and what is the specific volume, what is the entropy, and all the properties can be obtained at this point. Okay. Similarly, all the properties at 0.3 can be obtained just from this temperature and the quality, because it is a saturated liquid. Okay. So, these properties also can be obtained directly from the refrigerant database, or if you have a pH chart, you can directly locate these points. Okay. And from the pH chart, you can find out what is the condensing temperature and what is the evaporating temperature once you know the condensing and evaporating temperatures. Okay. So, we know the pressures and we know the properties at 0.1 and 3. Now, how do you find the property at 0.2 dash? 0.2 dash lies in the superheated region. So, if you want to find the properties, you have to specify two independent properties. Okay. So, what are the properties we know? We know the pressure at this point. Okay. We know P2 dash. Okay. P2 dash is nothing but condenser pressure, which is the pressure at saturated pressure at 54.4 degrees centigrade. This is known to us. Okay. So, at this point we know the pressure. What else we know? We know that process 1 to 2 dash is isentropic process. That means the entropy at 0.2 dash is same as entropy at 0.1 dash. That means we also know the entropy at this point, because we know the entropy at 0.1. That means S2 dash is equal to S1. This is known. Okay. So, at 0.2 dash we know two independent properties, that is pressure and entropy. So, we can find out from these two independent properties rest of the properties such as temperature, enthalpies and all that. Okay. So, that is how you can find the properties of 0.2 dash. Once you find the properties of 0.2 dash, properties at 0.2 can be obtained, because at 0.2 we know that P2 is equal to Pc, which is known to us, and H2 is the enthalpy at this point. Enthalpy at this point is nothing but from the expression of isentropic efficiency, it is the inlet enthalpy plus H2 dash minus H1 divided by isentropic efficiency of the compressor. Okay. So, H1 is known to us, H2 dash is known to us also, and this is given as input. So, we can also find out the enthalpy. So, for this point, use the pressure data and enthalpy data and find out the rest of the properties. Okay. Now, coming back to 0.1 dash, 0.1 dash is nothing but the saturated liquid at evaporated temperature. So, straight away you can locate this point, because you know the temperature and you also know the pressure, and you know that it is in saturated condition. Okay. That means you have to locate this point on the saturated liquid line. So, you can find out enthalpy and all other properties. And finally, coming to the 0.4. Okay. 0.4 is nothing but the inlet to the evaporator, and what do we know at this point? At this point we know what is the pressure, and we also know the temperature. But can you find out from this pressure and temperature what is the enthalpy and rest of the properties? You cannot, because this is a two phase region. So, if you are fixing the pressure, temperature is automatically fixed. That means pressure and temperature are not independent properties in the two phase region. Okay. So, specifying both is meaningless. Okay. So, you have to, or useless. So, you have to specify any one and another property. What is that other property? That property is enthalpy, because we know that this process is a throttling process. So, for this process H3 is equal to H4. Okay. So, H3 is known to us, that means H4 is also known to us. That means at this point we know the pressure PE and we know the enthalpy H4. Okay. So, from these two properties you can find out the rest of the properties like entropy, specific volume and all that. Okay. So, that is how you have to find the properties at various points. So, it is always useful to draw the cycle on a pH diagram and list what the points you know and have an idea of the different processes. Okay. Then you can straight away read the missing data points. Okay. So, using this procedure, this is the data obtained for various points. State point 1, which is the outlet of the evaporator or inlet to the compressor, temperature is minus 23.3 degrees centigrade specified, and pressure is nothing but the saturation pressure at this point is 1.148 bar, and we know that it is saturated vapor. So, quality is 1, which is known to us. So, if you are using this information from the pH chart or from refrigerant property database, you find that enthalpy is 384.5, entropy is 1.744 and specific volume is 0.169. Okay. Similarly, the data for other points at point 2 dash, which is nothing but the exit of the isentropic compression process, we know the pressure which is equal to 14.7 bar. And we also know the entropy, which is same as the entropy at point 1, that is 1.744. So, from the pressure and entropy data, we find the rest of the points, that is the temperature and enthalpy. Okay. Point 3 is the exit of the compressor and inlet to the expansion device. Here we know the temperature, which is equal to 54.4. So, the pressure is 14.7, which is the saturation pressure at this temperature. And we also know that it is saturated liquid. So, quality is known to us, that is 0. So, from the quality and the temperature, find out the rest of the properties like enthalpy and entropy. Okay. And then comes point 4, which is the exit of the expansion device or inlet to the evaporator. So, at this point, as I have already told you, we know the temperature and pressure, and we also know the enthalpy, because the enthalpy at point 4 is same as the enthalpy at point 3. Okay. So, using the pressure and enthalpy data, we find the rest of the properties, that is entropy and specific volume. And point 1 dash is the saturated liquid condition at evaporator temperature. So, we find out the enthalpy and entropy and specific volume at these conditions, and finally find out the actual temperature and enthalpy at the compression process, okay, at the exit of the compressor for the actual compression using the isentropic efficiency. Okay. So, this is how all the state points have been obtained. So, using this state point data, we will find the required performance parameters. One thing I would like to mention here is the enthalpy and entropy values may vary from database to database. Okay, because if you remember, enthalpy and entropy are generally defined with reference to a particular datum. Okay, if the datum is different, these values can be different. Okay, whereas the rest of the properties will be same for all the property databases or all types of pH charts. Okay, so you need not worry if the enthalpy and entropy values are different from source to source. Okay, because in our calculations ultimately we will be requiring the enthalpy difference or entropy difference. Okay, since you will be using the differences, the reference enthalpy or reference entropy really does not affect the final answer. Okay. So, now we know all the points. So, we find out the mass flow rate of refrigerant, apply the energy balance across the evaporator. From the energy balance, we find that mass flow rate is equal to QE divided by H1 minus H4. QE is known to us, this is 0.1 kilowatt, and H1 and H4 have been obtained from the refrigerant database. Okay. So, this will give us mass flow rate as 9.434 into 10 to the power of minus 4 kg per second. And volumetric flow rate at compressor inlet is nothing but mass flow rate into specific volume at compressor inlet, which is known to us. So, you find that volumetric flow rate is 1.594 into 10 to the power of minus 4 meter cube per second. And then quality of refrigerant at evaporator inlet. So, what do we mean by quality? We have already defined the quality. Okay. So, quality is at evaporator inlet is at this point. So, quality at this point is defined as mass of vapor divided by total mass, that is mass of vapor plus mass of liquid. Okay. You can show that this is equal to H4 minus H1 dash divided by H1 minus H1 dash. Okay. This is also equal to, you can write this in terms of, for example, specific volume, that means V4 minus V1 dash divided by V1 minus V1 dash. That means the quality can be expressed in terms of any intensive property such as enthalpy or specific volume or entropy. Okay, that is what is required. Since we know the enthalpies, we let us write this in terms of enthalpies. We know the enthalpy at 0.4, this is known because this is equal to H3, and H1 dash is known and H1 is also known. Okay, so we use that expression. to find the quality. So, quality is found to be x4 is equal to h4 minus h1 dash divided by h1 minus h1 dash, which is equal to 0.5072. Okay. Then void fraction. Void fraction is defined as the volumetric flow rate of vapor divided by the total volumetric flow rate. So, the difference between quality and void fraction should be clear. Quality is in terms of mass flow rates and void fraction is in terms of volumetric flow rates. Okay. So, the volumetric flow rate can be expressed by multiplying the mass flow rates into specific volumes. So, if you do that, you find that the expression for void fraction is given like this: phi 4 is equal to V1 into x4 divided by V1 dash plus x4 into V1 minus V1 dash, and we know all these specific volume from properties. So, you find that volumetric flow rate is 0.9597. That means more than 95% of the volume is occupied by the vapor. And actual power input to the compressor, as I have already explained, is nothing but isentropic work input divided by the isentropic efficiency. We know the isentropic work input, which is equal to mass flow rate into enthalpy difference for the isentropic process divided by the isentropic efficiency 0.65. So, if you substitute these values, you find that the actual power input is 0.07736 kilowatt or 77.36 watts. Okay. Compressor discharge temperature. Discharge temperature can be obtained because we know that at the compressor discharge the pressure and enthalpies are known to us. So, using the pressure and enthalpy data, we can find out the compressor discharge temperature, and this is found to be 89.97 degrees centigrade. Okay. So, finally, we have to find out actual COP. Actual COP is defined as QE by W actual. QE is 100 watts and W actually is 77.36 watts. So, you find that actual COP is 1.293, and the cycle efficiency is COP actual divided by COP Carnot, and COP Carnot, as you know, is nothing but evaporative temperature divided by condenser temperature minus evaporative temperature, and all the temperature should be expressed in absolute scale, that means in degrees Kelvin. So, if you are writing this in degrees Kelvin, you find that COP Carnot is 3.216. Okay. So, from this you find that the cycle efficiency is 0.402. Okay. So, this is a very simple problem, and the whole idea of working out this problem is to show how properties at various state points can be obtained, and how the required performance parameters can be obtained by applying proper energy balance equations. Okay. So, let me explain the third problem. The third problem is another simple problem. This is a saturated single stage cycle and a SSS vapor compression refrigeration system based on refrigerant R134A operates between an evaporator temperature of minus 25 degrees centigrade and a condenser temperature of 50 degrees centigrade. So, evaporator and condenser temperatures are specified, and assuming isentropic compression, we have to find COP of the system, find work input to compressor, and find area of superheat horn, and finally find the throttling losses. Okay. And assume that the isobar at condenser pressure to coincide with saturated liquid line. So, this is the information given to us. Okay, this is a standard vapor compression refrigeration system. Here it is convenient to represent this on TS diagram. So, you can see that on TS diagram cycle 1, 2, 3, 4 is your SSS cycle. Okay. So, 1 to 2 is your compression process, 2 to 3 is heat rejection in the condenser, 3 to 4 is throttling process, and 4 to 1 is isobaric isothermal heat extraction. Okay. And if you remember from our earlier discussions, the heat loss due to superheat horn is given by this. Okay. That means area 2 2 dash 2 double dash. This is the loss due to superheat horn, and loss due to throttling is given by this area. Okay. And if you are assuming that this saturated liquid line coincides with the isobar at this, that means it coincides with the isobar at PC, then this is also equal to throttling area. Okay. That means throttling area is either 1 dash 3 4 dash, which is equal to area CD 4 4 dash. Okay. So, we have to find out these two areas. Before finding that, we have to find out the state points at various locations, that means 1 2 dash 2 etc., and we know this temperature to be minus 25 degrees centigrade, and this is to be 50 degrees centigrade. So, we can find out this evaporator pressure and condenser pressure PC, because they are the saturation pressures at these temperatures, and we know that this is a saturated cycle. So, we can find out the data at point 1 which is the outlet of the evaporator, and inlet to the compressor, which is in saturated vapor state at evaporator temperature. Similarly, you can find out the properties at point 3, which is the exit of the condenser, which is in saturated liquid region. So, these 2 points we can easily obtain. And point 2, at this point we know the pressure, okay, pressure is equal to condenser pressure. So, we can find out this, and we also know that this is an isentropic process. So, S2 is equal to S1. Okay, so you can we know completely about point 2, so you can find out rest of the properties. And point 2 double dash, you can see that this has a temperature same as the condensing temperature, that means T2 double dash is equal to 50 degree centigrade, that is known, and we also know that S2 double dash is equal to S1. So, we know again 2 properties, so we can find out rest of the properties. And point 2 dash is nothing but saturated vapor at 50 degree centigrade. So, you can easily find out the properties, other properties. And point 1 dash is the saturated liquid at minus 25 degree centigrade. So, this point is uniquely fixed. So, you can find out all other properties. And point 4, at point 4 you know the pressure PE, and you also know that it is an isenthalpic process. So, the enthalpy at point 4 is same as enthalpy at point 3, that means H4 is equal to H3, which is known. So, you again know everything about point 4. So, you can find out rest of the properties. Point 4 dash, as you can see from the drawing, has same entropy as that of point 3, that means S4 dash is equal to S3. Okay, so the which is known to us, and we also know the pressure at this point. Okay, that means from the given information you can find out the property data at all these points. Okay, so now let me show this property data. Before that, this is the summary of the information given. Refrigerant is 134A, evaporator temperature is minus 25 degree centigrade, and condensing temperature is 50 degree centigrade. Okay, and the property data, as I have already explained, is like this. This is the exit of the evaporator or inlet to the compressor. We know this temperature and quality, so we can find out the pressure, saturation pressure, and then we can find out the enthalpy and entropy from the pH chart or from the TS chart or from any other database. Next, point 2 is isentropic compression. We know the pressure, which is corresponding to 50 degree centigrade, saturation pressure corresponding to 50 degree centigrade, and we also know that it is isentropic process, so the entropy is same. So, these 2 are known to us. So, find the rest of the properties. Similarly, point 3 is the exit of the condenser. We know the temperature and we know the quality. So, find the pressure, find the enthalpy, and find the entropy. Point 4, okay, it is the exit of the isenthalpic process. So, the enthalpies are same at point 3 and point 4, which is known to us, and we know that the temperature is minus 25, which is same as the evaporator. Pressure is also known to us. So, from this we can find out what is the entropy. Okay, and you can also find out the exit quality from these enthalpies. And point 1 dash is saturated liquid at evaporator temperature. So, you can find out easily enthalpy and entropy. Point 2 dash is the saturated vapor at 50 degree centigrade. You can see that saturated vapor, quality is 1, temperature is 50 degrees, pressure is 13.18. So, you can find out the rest of the properties. Point 2 double dash, at this point we know the temperature, which is equal to 50 degrees, and we also know the entropy, okay, because this lies on the constant entropy line. So, this is known to us, this is known to us. So, rest of the things we can find out. Finally, point 4 dash, at point 4 dash we know that the temperature is minus 25, and we know that at this point the entropy is same as that of point 3. Okay, so, this is same as 1.37. So, we know the 2 properties, so we can find out the rest of the properties. So, that this is how we found the properties at all the points. So, once you find the properties at all the points, you can easily calculate COP. COP is nothing but refrigeration effect H1 minus H4 divided by specific work of compression, that is H2 minus H1, which is found to be 2.1174. Then work input to compressor is nothing but H2 minus H1 from energy balance across the compressor, so which is found to be 52.8 kilojoule per kg. Then we have to find the superheat horn area. Okay, superheat horn area is area A1, and it is nothing but area under 2 dash minus area under 2 double dash to 2 dash. Okay, let me explain this. Okay, so this is the superheat horn area, the hatched area. Hatched area is nothing but area under 2 dash, that means the complete area, this entire area, minus area under 2 double dash to 2 dash, that means this area. Okay, so if you can find out the area under curve 2 to 2 dash and subtract the area under the curve 2 double dash to 2 dash, you get the superheat horn area. Okay, and this is an isobaric process, that means P2 so I will quickly explain how we can calculate this superheat horn area. Process 2 to 3 is an isobaric process, that means P2 is equal to P2 dash, and remember that we know all the entropies and all the state point properties are known to us. So area under the curve 2 2 dash, okay, area under 2 2 dash is nothing but integral TdS from 2 to 2 dash. Okay, and from thermodynamic property relations we know that TdS is equal to dH minus VdP. Okay, so if you are applying this relation to this particular process 2 to 2 dash, you find that VdP is equal to 0, because the pressure does not change during this process, this is an isobaric process. So finally you find that TdS is equal to dH, that means integral TdS from 2 to 2 dash is nothing but integral dH from 2 to 2 dash, which is simply equal to H2 dash minus H2. Okay, if it is as simple as that. So if since we know the enthalpies, we can easily find out, and this remember is nothing but the entire area, okay, under the curve. And what is the area under curve 2 double dash to 2 dash? Area under 2 double dash to 2 dash is nothing but this rectangular area. Okay, so which is equal to again integral TdS from 2 double dash to 2 dash, and this is an isothermal process, so temperature remains constant. So this is simply equal to Tc into S2 dash minus S2 double dash. Okay, and we know the entropies at these points, and Tc is known to us, so you can also easily find out this area. Okay, so it's very easy, we just find out the area under 2 dash and area under this one and subtract these two areas, you will get the superheat horn area. Okay, now how do you find the throttling area? Okay, throttling area can be obtained in by two ways. Okay, the first way is if you are finding the proper throttling area is this is nothing but throttling area from this expression is nothing but CD 4 dash or nothing but the rectangular area, and this is equal to again if you are applying integral TdS, temperature remains constant, integral TdS from 4 to 4 dash. So this is simply equal to TE into S4 minus S4 dash. Again we know all the entropy, so you can easily find out the throttling area using this expression. You can also use the throttling, find out the throttling area from this side. Okay, because if you are assuming this line to coincide with the isobar at PC, this also happens to be the throttling area, and if this is the throttling area, okay, if you are calculating it from this side, this is nothing but area under 3 to 1 dash, area under 3 to 1 dash minus area under 4 dash to 1 dash, 4 dash to 1 dash, that is this area. Okay, and area under 3 to 1 dash, you can see that for this again area under 3 to 1 dash is integral TdS from 3 to 1 dash, which is equal to, again you can use the expression dH minus VdP, TdS is Vh minus d, and since we are assuming that this line is an isobaric line, VdP is 0. So this simply becomes TdS becomes equal to dH. So finally this is nothing but H3 minus H1 dash. Okay, so we can easily find out, and this rectangular area, that is area under 4 dash 1 dash, is nothing but TE into S4 dash minus S1 dash. Okay, so that's how once you have the cycle diagram, you can easily find out the required areas. Okay, so that is what is done here. Okay, so I have explained this procedure. All this is shown to you, and if you are substituting the values, you find that area under 2 dash is found to be 12.8 kilojoule per kg, and area under 2 double dash to 2 dash is nothing but the rectangular area, is found to be 12.6 kilojoule per kg. So from these two we find that the superheat horn area is equal to 12.8 minus 12.6, that is 0.2 kilojoule per kg. Okay. Now let us find out the throttling area. So I have, as I have already explained how to find the throttling area. If you are assuming that the saturated liquid line is coinciding with the isobar at condenser pressure, then it is the area under 3 to 1 dash minus area under 4 dash 1 dash. Okay, so this is the expression. Area under 3 to 1 dash is nothing but H3 minus H1 dash, and area under 4 dash to 1 dash is nothing but TE into S3 minus S1 dash, because S4 dash is equal to S3. Okay, so since we know all these values, you substitute these values, you find that the throttling area is 14.47 kilojoule per kg. If you are finding the actual throttling area without making this assumption, then that is given by area under 4 to 4 dash, which is equal to TE into S4 minus S4 dash, and this works out to be 14.4 kilojoule per kg. You can see that the assumption that the isobar coincides with the saturated liquid line is reasonably good, because these two values are perfectly matching. Okay. Now you can also check the your results, because we know that for the single stage saturated cycle, the work input is equal to work input of a Carnot cycle plus area A1 plus area A2. Okay, and what is the Carnot cycle? Carnot cycle here is an equivalent Carnot cycle is 1, 2 dash, 3, 4 dash. So this is your Carnot cycle. So find out what is the work done during this Carnot cycle. Work done during this Carnot cycle is nothing but this. Okay, which is equal to Tc, this is Te, this is equal to the rectangular area, that is Tc minus Te, into this entropy difference. Okay, that means S1 minus S4 dash. We know all these things, you can easily calculate the work input to the Carnot cycle, and work input to the actual cycle is work input to the Carnot cycle plus this area plus this area. Okay, so you can check your result. So if you are doing that, work input to the Carnot cycle is found to be 38.2 kilojoule per kg, and work input to the standard cycle from this expression is 38.2 plus 14.4 plus 0.2, which is working out to be 52.8 kilojoule per kg, which matches exactly with the data obtained earlier. Okay. Now you repeat this problem. The homework is like this: repeat the problem by replacing R134A with ammonia, and you compare the performance, and you conclude by comparing the results obtained with R134A and ammonia. Okay, so there will be some differences because ammonia has a different TS shape. Okay, vapor dome shape is different on TS plane for ammonia and 134A. Okay, so this is the homework, right? Now let me quickly give some objective type problems for your homework. Okay, so objective problems are like this. First problem is, which law of thermodynamics is a directional law? The answers are: A is first law, B second law, C third law, fourth zeroth law. Okay. The second question is, according to second law of thermodynamics for a system undergoing a process, entropy of the system cannot decrease, that is A, and B is entropy of the system cannot increase. C is the sum of entropies of system and surroundings remains constant, and D, the sum of entropies of system and surroundings always increases. And third question is, expansion of liquid always results in a significant temperature drop when the initial condition is in subcooled state, the initial and final conditions are in subcooled state, the final condition is in two-phase region, and none of the above. And fourth problem is, during isenthalpic expansion of a real gas with negative Joule-Thomson coefficient, the final temperature is lower than initial temperature, the final temperature is higher than initial temperature, the final temperature is equal to the initial temperature, and finally nothing can be said about the temperature. And problem number 5, the COP of a completely reversible single stage refrigerant system depends only on the evaporator and condenser pressures, depends only on the evaporator and condenser temperatures, depends on the working fluids and operating temperatures, and all of the above. Okay, I will give the answers to these problems in the next class, and I will also work out 1 or 2 problems on vapor absorption systems in the next class. Thank you. Welcome back. In this lecture I will work out few more example problems and I will also give answers to the questions given in the last lecture. So, the first let us go to the first problem. The first problem is like this: in a R22 based refrigeration system, a liquid to suction heat exchanger with an effectiveness of 0.65 is used. The evaporating and condensing temperatures are 7.2 degrees centigrade and 54.4 degrees centigrade respectively. Assuming the compression process to be isentropic, find specific refrigeration effect, volumic refrigeration effect, specific work of compression, COP of the system, and finally compressor exit temperature. And comment on the use of liquid suction heat exchanger by comparing the performance of the system with a SSF cycle operating between the same evaporator and condensing temperatures. That means basically it is a single stage system. We have to make performance comparison between a system with liquid suction heat exchanger and the system without liquid suction heat exchanger. Both of them are operating between the same evaporator and condensing temperatures. Now, let us see how. Then work of compression. Work of compression, obviously with liquid suction heat exchanger, work of compression has increased because the isentropes in superheated region are flatter compared to the isentropes closer to the vapor dome. So, this is 36.1, this is 31. So, this is actually a negative this thing. And COP you can see that is almost same, okay, it is 4.465 with liquid suction heat exchanger and it is 4.455 without liquid suction heat exchanger, okay. This is because COP, as you know, is the ratio of refrigeration effect divided by work of compression. So, when you are using liquid suction heat exchanger, refrigeration effect is increasing, work of compression is also increasing, okay. And without liquid suction heat exchanger, this is less. At the same time, work of compression is also less, okay. So, as a result, the net difference between these two is not much, okay. And however, one significant difference between the system with liquid suction heat exchanger and without liquid suction heat exchanger is in the discharge temperature, okay. You can see that with liquid suction heat exchanger, discharge temperature is about 105 degrees centigrade, whereas without liquid suction heat exchanger it is about 74 degrees centigrade. That means almost more than 30 degrees increase, okay. So, this is definitely a negative point as far as the liquid suction heat exchanger is concerned, okay. So, you have when you are using liquid suction heat exchanger, particularly for R22 systems, there are some benefits and there are some disadvantages, okay. So, ultimately depending upon your requirement, one has to decide whether liquid suction heat exchanger is required or not, okay. And one